All right, I wanted to look at this example a little bit more. So this is the example where we have a population with three values, 1, 2, and 3. So it's a very, very simple, very small population. And what we're going to do is consider taking samples of size n equal to 2 with replacement from this population. And the purpose of this is to consider the sampling distribution of the sample mean and look at characteristics of that sampling distribution. So we looked at this in a fair amount of detail, and I wanted to show you one more thing that you can use to do the calculations that are involved in this. And so we're not going to spend a lot of time on this because we have looked at it in a fair amount of detail. But just to reiterate, the first thing that we were supposed to do was to find the mean, the variance, and the standard deviation of this population. All right, and so we've done that. The population mean, which is denoted by mu sub x, is equal to 2. The variance of the population, which is sigma squared sub x, is 2/3. And so the population standard deviation is the square root of that variance, the square root of 2/3. All right, and so then we are to consider taking samples of size little n equal to 2. Remember that in the notation that we're using in this class, capital N is the size of the population, if it's a finite population, and most in this course will be. And then we're using little n to represent the size of a sample. And so in this situation, we are considering taking samples of size little n equal to 2 with replacement from this population. And the fact that we're taking the samples with replacement is very, very important. And so the next task is to find the sampling distribution of the sample mean for samples of size little n equal to 2. Again, the samples taken with replacement. And so remember that the sampling distribution is just the probability distribution for the sample statistic that we are talking about. All right, and so we have this schematic that we looked at, and so we have our population up here, all right, the mean of which is 2, the variance is 2/3, and then we saw that there are 9 possible samples that we could select from this population when we're sampling with replacement. All right, and then associated with each of these samples is a sample mean, for example, which I've got listed under each of these samples. We could also have calculated the sample variance for each of these. We didn't do it on this page. We did it on the table template that we looked at, that we used. Okay. Our focus right now is on the sampling distribution of the sample mean, and so that's why I have included only the sample means here. And then from these, well, let me also say that because of the way that we are selecting the samples, we're selecting them at random and with replacement, then what that does is it causes each of these 9 samples to be equally likely. And so each one has a probability of 1/9 of being selected. And so using that information, along with the possible values for x bar, we see that there are 5 unique values that the sample mean can take on in this situation. 1, 3/2, 2, 5/2, and 3. Then using that information, along with the fact that these 9 possible samples are equally likely, we come up with the probabilities associated with each of the values of x bar in its sample space. And so this table, containing 2 columns, is a tabular representation for the probability distribution for x bar in this situation. In other words, it's a tabular representation for the sampling distribution of x bar for samples of size little n equal to 2 taken with replacement from this population. And so that is so we've done that right here. This first bullet point, we've accomplished that. And then we were to find the mean, the variance, the standard deviation, and so forth for the sample mean for samples of size little n equal to 2. So that is the next task that we are going to accomplish, and we can use the sampling distribution that we've got here to do that. And so anyway, I'm scrolling down here, and so here it was the calculation that we used to calculate the mean of the sampling distribution of X bar. All right, so remember that the mean of a discrete probability distribution is a weighted average of the values taken on by the random variable. And the weight factor is the PMF, or the sampling distribution values for the various values that the random variable can take on. And so the values that the random variable X bar can take on in this situation, you'll remember, are 1, 3/2, 2, 5/2, and 3. The corresponding values for the PMF of X bar, or the sampling distribution of X bar, evaluated at those values would be 1/9, 2/9, 3/9, 2/9, and 1/9. And so then we calculate this weighted sum, all right, which is also a weighted average because the sum of the weights is 1, all right, and we get 2. So that is the mean of the sampling distribution of the sample mean X bar. All right, and then we have to calculate the variance of the sampling distribution. And so we used the computational formula to calculate the variance. And so we first had to calculate the expected value of X bar squared. All right, and so that was done using this calculation. And then once we had done that, then using that value, the expected value of X bar squared, and also the expected value of X bar, which we had just computed previously, we have to square that value and then subtract that from the expected value of X bar squared. And so when we did that, we came up with 1/3. All right. And then finally, once we have the variance of the sampling distribution of X bar, then we can find the standard error of X bar, which is the standard deviation of the sampling distribution of X bar, by calculating the square root of the variance. All right. Remember that the standard deviation is always the square root of the variance. And so the standard error of X bar, also known as the standard deviation of the sampling distribution of X bar, is the square root of 1/3. So those are the calculations that we performed using the sampling distribution of X bar. We can think of a probability distribution like this as being a summary, a condensation of the values that a random variable can take on. And so this PMF, this probability distribution, this sampling distribution, is a concise way, it's a condensation of the probability structure that exists on this entire sample space. All right? And so we can calculate the characteristics of this distribution using the PMF, but we could also just use all of these values without condensing them first. And so that was the other method that we used to calculate the mean, the variance, and the standard deviation of the sampling distribution of X bar for this situation. And to use that more expanded approach, we used this template table. All right. And there were 9 possible samples that we could have in the situation. And so I've created this template so that it has 9 rows in the body of the table. And then underneath, we've got some rows for summaries, right? But in terms of the body of the table, we have rows for the 9 samples. And then what we did was we filled in the sample number column, 1 through 9, and then we filled in the next 2 columns that contain the values for the 9 possible samples. Okay, and from there we can calculate some summary information. We can also calculate the mean of each sample, the variance of each sample, and we also calculated the product of the values, x1 times x2, for each sample, and we did that. That helped us calculate the covariance of x1 and x2 in the sampling distribution. So that is how we calculated or used this table template to calculate these quantities. We saw that based on this, on the way that we're sampling, the mean, the expected value of x1 across all samples was 2. The expected value of x2 across all samples was 2. The variance of x1 across all samples was 2/3. The variance of x2 across all samples was 2/3. And this is the way it should be because these are coming from the population. And notice that these are population, 2 is the population mean, and 2/3 is the population variance. So x1 has that distribution, that population, and so it has the same quantities. Now, or the next thing we did was calculate the sample mean. All right, and so these are the values that we get in the first 9 rows. All right, for the sample mean, and then to obtain the mean of the sampling distribution of x bar, all we had to do then, using this information, was to calculate the population mean of these values, and that mean value is 2. Okay, and then to find the variance of the sampling distribution of x bar, we calculated the population variance of those 9 values. All right, and we're using the population variance formula because this is the full set of possible values that x bar can take on. So it's the population of possible values for x bar. Right, the first 9 rows here. And the population variance of those values of x bar is 1/3. And so that tells us then that the variance of the sampling distribution of x bar for this situation is 1/3. So that is the way that we can calculate the mean and the variance of the sampling distribution of x bar by using this expanded approach. Instead of using the condensation, using all of these, all 9 samples. And so we have found then, using that approach, that the mean of the sampling distribution of x bar is 2. The variance of the sampling distribution of x bar is 1/3. And then we also pointed out in this example that the mean of the sampling distribution of x bar is equal to the mean of the population from which the samples are being obtained, and that the variance of the sampling distribution of x bar is equal to the variance of the population that we're sampling from, 2/3, over the sample size, which is 2. 2/3 over 2 is 1/3, all right, and so we found this relationship. And the question was, are these two results a coincidence, or is there some underlying principle at work here? And we found that this is not a coincidence. This will always be the case for this particular type of sampling. And what is this kind of sampling? Well, we call it IID sampling, independent and identically distributed sampling. And so IID sampling is used when, or is being performed if you're sampling from an infinite population, or if you happen to be sampling from a finite population, you're sampling with replacement. And so that is why specifically stating that we were sampling with replacement was an important piece of information for us. So these two results will always hold when we're performing IID random sampling. So we used this table, all right, to come up with those values. This is another approach. Using this table, this tabular kind of approach, where we're considering all, where we're listing all possible samples, frees us from having to create the condensed version, which is the actual PMF or sampling distribution. All right, you can do it either way, but if sometimes this kind of approach that I'm showing here will be easier. Now, before we go on, let me just say that we also in addition to the sample mean, we calculated the sample variance, all right? And we also calculated for each sample the product of x1 and x2, all right? And we filled those values in. And then we calculated the mean. We did not calculate the variance for those values. We could have, but it really did not serve a purpose for us at this point. But we did calculate the mean of the variance column as well as the x1 times x2 column. Now remember that, for example, that the mean value of the column of x1 times x2 values, that value of 4, that was, this is the expected value of x1 times x2. And we use that in calculating the covariance of x1 and x2. In fact, if I go to this slide here, this is what that 4 represents in that table. It's the expected value of x1 times x2. Now we also have the mean value of the column of sample variances. Now remember that the sample variance, this is the version of the sample variance that has n minus 1 in the denominator, all right? And when we do this, when we calculate the variance in that way, right, which is the way that you learned how to calculate the sample variance in your first methods class or classes, then notice that the average of those possible values for the sample variance, so from here down to here, the mean of those is 2/3. Well, that is remember that 2/3 is the value for the population variance. And so what this shows is that the expected value of S squared is equal to the population variance. And again, remember our discussion about what it means for an estimator to be an unbiased estimator. An estimator of a population parameter is an unbiased estimator if the mean of its sampling distribution is equal to the parameter itself. All right, and since the expected value of S squared in this case is 2/3, which is the population variance, we see that at least in this example, for this population and this sampling procedure, that the sample variance is indeed an unbiased estimator of the population variance in this example. And it turns out that that is always going to be the case for this, again, for this particular type of sampling, which is IID random sampling. And in fact, that is the reason that we use the version of the sample variance that has n minus 1 in the denominator, because doing so under IID random sampling makes that version of the sample variance an unbiased estimator of the population variance. In fact, that is what we were showing on this slide when we discussed the sampling distribution of the sample variance. We see here the formula for this version of the sample variance, the version that has n minus 1 in the denominator. And what we are stating here is that what we saw in this example is not unique to this example. It's again a general result. Whenever we are performing IID random sampling, then the version of the sample variance that has n minus 1 in the denominator is an unbiased estimator of the population variance. In other words, the expected value of that random variable is equal to that population variance. In other words, the sampling distribution of the sample variance is centered right where it needs to be, right at sigma squared. So these are results that are really important for us to know and understand, all right, because it's the basis for the estimators that we actually use in the context of IID random sampling. Now going back to the table template that we filled out, and I want you to do this example on your own. And so I have posted this template, an empty version of the template, on Moodle, and so I would like you to download that and work through the calculations on your own. One additional thing I wanted to show you, all right, is in using this same kind of approach. But this approach is really conducive to implementation on, say, a spreadsheet. And so here is an example of a spreadsheet that I created for this particular example. And it has a very similar format to the template table. It has a few more columns, all right, that we don't need to worry too much about right now. But I do want to show you, so I've got the description of this spreadsheet. This is for the sampling distribution of the mean of random samples taken with replacement of size n equal to 2 and from the population of size cap n equal to 3. So here I have the population values. Now I know that it may look like this column, everything down below this corresponds to that population value, and everything below that belongs to that population value, and so forth. That's not the case. This information about the population is really separate from the values down here. Okay, so, but we do see, I do give, I guess, the population size, the population mean, the population variance, and the population standard deviation. So this is information, this is calculating, it lists the population, and it is calculating the population characteristics. Then underneath the area for the population, I've got an area where I list all 9 possible samples, all right, and then I have the sample values for x1 and x2, and those are entered by hand, all right, but everything to the right and down below is programmed in, so I'm able to very easily calculate the sample mean for each sample, the variance of each sample. I've also got the standard deviation, the sample standard deviation here. Like I said, I have a few extra columns that I don't include in the table template. We really don't need those at this point, but I do have the column for x1 times x2. All right, and again, these are all very easily programmed in so that once you enter the values for the random variables for each sample, then everything else gets populated, gets calculated automatically. All right, and then down below this, I have some summary statistics, summary calculations. So I have the sum, just like the table template. I've got the sum of the values. I have the population mean of the values. I also have the population variance and standard deviation. Now, let me just point out, you have to be very careful. In the columns, notice that I've labeled the columns that I'm pointing to here, sample variance and sample standard deviation. And so there are functions that are specifically to calculate variance and standard deviation when you consider the data set or consider the values to be from a sample. All right, so you have to use the sample version of those functions, the sample variance and the sample standard deviation. But remember that when we are considering all 9 possible samples, we consider that to be the population of the sampling distribution, possible values. And so the variance and standard deviation that we're calculating down here are the population counterparts to those functions. So the population variance and the population standard deviation. All right. So again, all of these quantities down here are programmed into the spreadsheet using the built-in functionality, the built-in functions of the spreadsheet software. Now I happen to be using OpenOffice, the OpenOffice spreadsheet, but Excel has the same functions, and so you could program this in Excel as well. Notice that I also have formulas for the covariance and the correlation, and I don't believe, it's been a while since I've done this, but I don't believe that functionality is actually built in via a function. I had to actually take the mean value of x1 times x2, so this value, remember that's the expected value of x1 times x2, and then from that subtract the product of the expected value of x1, which is 2, and the expected value of x2, which is also 2 there. So take the value in this cell, from it subtract the product of the values in those two cells, and that gives me the covariance. To get the correlation, we divide the value in this cell by the square root of the product of the values in this cell and this cell. So the variance of x1 and the variance of x2. Okay, so that is how this spreadsheet is constructed. And although I have posted a copy of a blank copy of this table so that you can begin to work this out by hand, my very, very strong recommendation is that you create a spreadsheet like this for this example. And once you've done that, then this spreadsheet can serve as a template for doing the same kind of calculation for other examples that we may look at. And all you would have to do, if needed, is to either take out rows here or add rows to accommodate the total number of samples that are possible in a given situation. So again, creating a spreadsheet like this is going to be very, very, very helpful because it's going to relieve you of having to do all the tedious calculations. That's not the point of this kind of example. The point of this kind of example is to help you understand what a sampling distribution is and the impact that the type of sampling has on that sampling distribution. And so I will tell you right now that we are going to be looking at several examples throughout the semester where having this kind of a spreadsheet is going to be very helpful. And if you create a template, if you create this kind of a spreadsheet right now, it's going to be a big time saver for you because you can just tweak it, you can just modify it, you can use it as a template for other examples as we go through the course. And I will post a copy of this on Moodle as well so that you can compare your results. Once you do create a spreadsheet like this, you can compare your results to the results that I got. And again, at this point, we really don't need the x1 squared column and the x2 squared column. So if you don't want to include that, you really don't have to. But I would include everything else, including the column for x1 times x2, and make sure that you calculate or enter the formulas for the covariance and the correlation correctly. All right, so that is really all I wanted to talk about in this lecture video. What I really wanted to do is to really emphasize the importance of your creating a spreadsheet like this. And so I hope that you'll do that soon, and we will continue on in the next lecture video.